Hi everyone, my name is Sylvain Lézé from the Department of Aeronautics at Imperial College London, and this is a new episode of the podcast Turbulence at the exascale. So if you are not familiar with this podcast, we are talking about the challenges and opportunities associated with exascale computing for turbulence research, but not only, we are also discussing about turbulence research in general. So this podcast is part of the UK initiative called ExCALIBUR, which is a 5-year project designed to reconfigure and redesign the software infrastructure in the UK so that we are ready for the transition to exascale computing. And this podcast is also linked with the UK Turbulence Consortium. So today we have an international guest from France. His name is Jean-Christophe Loiseau. He is an assistant professor at DINFluid, which is a fluid dynamic lab, part of ENSAM. So ENSAM is an engineer school in Paris. It stands for École Nationale Supérieure des Arts et Métiers. So Jean-Christophe research is around turbulent flow, of course, machine learning, space regression techniques. And so it's going to be great to have a chat with him today. So good afternoon, Jean-Christophe.
Good afternoon, pleasure to be here.
Thank you very much. So I'm going to start this podcast with my usual question. If you can tell us a little bit more about yourself, where you're from, what you have studied, and how did you end up at the DINFluid lab?
So I'm French, even though my accent probably doesn't. I was born in France. I was raised pretty much all over the place, and at the end of high school, I had no really idea what I wanted to do, except that I had some appetite for physics. So I started back then in France. It was called a DUG. So that was a 2-year degree after high school in classical and fundamental physics. So I did a lot of like classical physics and also like the whole thing about quantum physics and general relativity and stuff. And that was nice. That was interesting. I really enjoyed it. But it was at some point it became a bit too esoteric for me, I'd say. And I had this introductory course to nonlinear physics and chaos theory, and that really got me interested. And so I decided to stop doing physics. And for my 3rd year, I moved to the applied math degree in Orléans, which is this town in the very center of France, where I really got into dynamical systems and some applied math. But I still had no real idea. I knew I didn't want to do hardcore math. I was not so much into like theorem proving and stuff. I was more into the applied side of it. And during this 3rd year, I had another introductory course to fluid dynamics and transition to turbulence in particular, where I realized I could apply most of the ideas I had seen from dynamical system theory to this problem of transition to turbulence. And also the figures were much nicer than what we had in physics. It was a lot of colors. So I decided to go for that. And so then for my master's, I did my first year actually part-time in Paris in fluid mechanics and part-time at Imperial College. I was at the chemical engineering department with Peter Spelt, who, well, unfortunately passed away recently. Where I did really hydrodynamic stability analysis of multi-phase flows. And for my 2nd year master degree, I was at École Polytechnique with Patrick Huer, who's like a pretty famous name in the stability community. And also Peter Schmidt was one of my lecturers, and he's really the one who got me hooked up to like the whole control and model decomposition stuff. And when it came to choosing a PhD, there was this proposal by Jean-Christophe Loiseau, who's now the head of DINFluid. And so I applied, and it was about stability of fully 3-dimensional flows. So we had to develop large-scale eigenvalue algorithms in NEC 5000, which is one of these pretty standard, I'd say now, HPC code for so that got me till 2014. And from then I moved a bit. So I moved to Italy for a few months with Bini and Pietro Di Palma at Politecnico di Bari, where I kept working on NEC 5000 and started to implement all the tools we needed to do non-linear optimal perturbation, which is one way to try to find the smallest perturbation that drives the flow to turbulence, basically. And after that, I went to KTH for 2 years, working with Luca Brandt on still stability analysis kind of problems, but for multi-phase flow. So we developed a code that could do multi-phase, two-phase, and adapt all the tools I had worked on during my PhD to try to extend these to multi-phase flows. And while I was there, a friend of mine who's not in fluid mechanics at all, he's in cognitive neuroscience, sent me a paper by Brenton, the 2015 PNAS paper about Cindy, and he wanted to get my feedback because he was a bit short on the math, so he just wanted to have my point of view on it. And he also told me, look, there's this example about this underflow, so it's applicable to fluid dynamics, so it might be of interest to you. And it definitely was, because I got in touch with Steve, and that's how I back into more the dynamical system reducer modeling point of view rather than really big computations. And in 2016, I got my position back in DynFluid in Paris. So DynFluid is it's a fairly small lab. We're just like 10 permanent positions, I think. And there, the core of my research still is focused essentially on incompressible stability analysis of pretty large scale flows. And on the other extreme, I also have this whole venue of research about reducer modeling. So how, instead of having to rely on HPC calculations, how can we do the same thing on a simple laptop for real-time control? So I'm trying to balance these two now.
Great, thank you very much. And may I ask you, so you did your PhD in Paris, then you moved a bit to Italy and to Sweden, and I was wondering what's the best thing about your job and your current position at DynFluid?
So I really like the liberty I have. So in France, compared to other countries, being an assistant professor, we have a lot of right? We have something like 200 hours per year, and that's quite a lot. But I really enjoy teaching, and I have the chance to have fairly simple courses like introduction to linear algebra and signal processing, for instance, for like first or second year students. And at the same time, I have this master course on dynamical systems. So that's very pleasant. That's something I really enjoy. It takes a lot of time. I'm not gonna lie, but it's really. And then DynFluid it's a pretty small lab, but we've all known each other for like at least 10 years now. And it's pretty great to work there. I really enjoy it. We have pretty complete liberty on to work on, and also, yeah, as someone who grew up abroad, the possibility to go to conferences and visit colleagues in other countries quite regularly is something I really enjoy.
Great, thank you very much. So you've already introduced us to your main areas of research. So can you tell us a little bit more about your recent work on transition to turbulence? You say you have been focusing on incompressible flows, but can you tell us a little bit more about what you're doing exactly?
All right, so we have these two different aspects. So the first one's really about the investigation of the instabilities and the underlying physical mechanisms that drives the flow to turbulence. And so for that, and we try to there's a lot that has already been done on flows like quad flow and quasi flows. There's still a lot we don't understand, but there's already quite a lot of tools available for that. And ever since the beginning of my PhD, we really put a lot of emphasis on complex geometries, or relatively complex geometries, and fully three-dimensional flows. And so on this side, we develop a bunch of tools that we'll probably discuss later on, to study the different bifurcations that takes place. So how the flow goes from being steady to time periodic, and how it goes from time periodic to quasi-periodicity, and then how chaos, and at least temporal chaos, because we're considering only low Reynolds number flows. So that's one aspect where we develop algorithms and also conduct physical analysis. So the latest stuff we've been doing has to do with jets and cross flows, essentially. I have a PhD who's finishing in a few months on this subject. And then the other aspect is reducer remodeling of this kind of systems, of flows, trying to have in mind that we want to be able to do these, I mean, these reducer remodels are used for controls, right? Real time, ideally would like to do real-time feedback control. It's not always feasible. And one of the problems for this feedback control is that you need to get an estimate of the state of the system, predict how the system's going to react to the action you're gonna take. And so obviously you would need if you want really high fidelity predictions, you would need to have on board the plane HPC cluster, which is absolutely not feasible. So we try to distill to their simplest form by using a combination of different techniques. Most of them are based on pretty well studied techniques like DMD, POD analysis, all these model decomposition that we try to push to their limit. And then with Steve, we've been working on the Cindy algorithm to identify governing equations from time resolved data, low dimensional data, where we try to use tools from machine learning, but also imbue them with physical knowledge or physical constraints to make sure that, well, the models we get are interpretable, so that as a physicist, you could say, right, this term is diffusion, this term is the coupling between, I don't know, buoyancy and the flow rate. And also trying to make sure they satisfy physical constraints. Like, for instance, if we apply this kind of techniques to Hamiltonian problem, we'll try to make sure that indeed the equation we get has an Hamiltonian. Or if we have a dissipative system, trying to make sure that dissipation is accounted for correctly. So that's the two different venues we have.
Great. So you mentioned already few software that you are using, but let's start with NextUp. So I've understand you have been using NEC 5000 quite extensively in the last few years, and so you have developed some sort of a stability analysis tools called NextUp. So can you tell us a little bit more about this NextUp?
Yeah. So well, first of all, NextUp, until recently, I hadn't realized I was a pun. That's Matthew Juniper back at APS a few weeks ago that really made me realize it. So that may be a terrible name, but we're focused on NEC 5000 and stability. It has nothing to do with stabbing people in the neck. So I've been working with NEC ever since I started my PhD back in 2010. And one thing I really enjoyed with NEC is that it's really simple to use. The whole interface is pretty simple. It has very little dependencies. It's extremely efficient. And whatever development you do, if it works on your laptop, it's very likely to work directly out of the box on the cluster. So this is pretty convenient. And so NextUp is basically, I'd say, somehow the pinnacle of my research tools that I've been developing over the past 12 years now. And it's a toolbox dedicated for NEC 5000. It's really a plugin for NEC. The philosophy and the methodology could be applied to other codes, but NextUp's really designed for NEC, where we've tried to put all the different algorithms we've developed regarding eigenvalue computations for stability problems, singular value computations for transient growth and resolvent analysis into a unified toolbox, and we try to make sure it's just to use as NEC. So it has the exact same dependencies. The only extra one is LAPACK, but which is, I mean, from the moment you have BLAS, you probably have LAPACK already installed. And over the past 3 years now with Ricardo, my PhD student, we've been working on extending it to stability of time periodic flows, so what we call Floquet stability analysis. And for that, we had to develop other tools like Newton solvers in a complete time stepper formulation to compute periodic orbits, periodic solutions. So that's what it is. It's basically a toolbox for NEC. We're wrapping up the paper as we speak. Toolbox, the code will GitHub available as soon as we submit the paper.
Yeah.
And the goal is really to make all these tools as accessible as possible, while trying to leverage all the benefit of NEC 5000, right? So we can do 2D stability, 2D flows, fully three-dimensional flows. There's also the temperature equation that can be included. It kind of works. There's still some debugging to do, but for instance, with the Lomax formulation that is available in NEC, all in a really simple user interface.
Great. Great. You briefly mentioned it, so I will come back to that. You mentioned the Floquet analysis that is possible to do with NextUp, but people who are listening to the podcast might not be familiar with Floquet analysis. So can you tell us a little bit more about it?
Sure. So we're basically interested in two different kind of let's say exact solution to Navier-Stokes. So there's what in the hydrodynamic community, there's what we call base flows, which are fixed points of the equations. So stationary solution to the stationary Navier-Stokes. And when you study these, the stability of these equilibriums, so you linearize the Navier-Stokes equation in their vicinity, and you get the Jacobian matrix, which we don't have access to in NEC directly. We only have the propagator for the linearized equation, but you can use a few linear algebra tricks to get the eigenvalues and eigenvectors, and these will tell you whether the solution is stable or unstable. Floquet analysis is really the same thing, but for time periodic solutions. So for instance, if you consider like the cylinder flow, there's the von Karman vortex street. This is a periodic orbit, what we call a periodic orbit or limit cycle of the equations. And you can study the stability of this particular kind of solution to infinitesimal perturbations. So it's the same thing. You linearize the equations, but now the matrix you get, the Jacobian matrix, is no longer constant in time. It's going to be time periodic. With all the coefficients are going to repeat themselves every tau time unit, what tau is the period of the vortex shedding, for instance. And so for the cylinder flow, if you do this kind of analysis, you get the famous mode A, which breaks the translational symmetry of the cylinder flow and create the three-dimensional vortex streets in 2D periodic simulations. So that's what Floquet analysis is. It's essentially extending the concept of linear stability from stationary solution to solutions that are periodic in time.
Great, thank you. And you mentioned in your earlier SIND or PySIND that you have been using as well with your colleagues in the US. So can you tell us a little bit more about this software?
So PySIND is a Python package for system identification. using the Cindy algorithm, which is this algorithm that Steve has been developing for the past now. So the idea of Piscini is really to have in a single package, in a single Python package, a unified interface for users, while making sure they can access all the different flavors of Cindy there are, because there's different flavors, whether you have noise or you don't have noise. You can add constraints in the identification problem to make sure the coefficient satisfies physical constraints, for instance. That's what I've been working on. There's recently we've actually just submitted a JOS paper with the Cindy 2.0 version, basically, where there's a lot of additional flavors that have been included. So it's a Python package. The idea was to make sure it's compatible with scikit-learn, which is the standard super famous package for machine learning in Python, so that we can also leverage this whole ecosystem. It's being essentially developed by students of Steve Branton in UW, in the University of Washington in Seattle, USA. The lead developer is Alan, which is doing a fantastic work. And yeah, so the idea is really you just time series data. It has to be low dimensional for some reason, but say you have the time series, the time dependent amplitude of your POD modes, for instance. And the idea is just you store them in a NumPy array and pass it to this package. And there's a few things here and there that you can choose, like the kind of library you will try to explain you're going to use to try to explain your data. So the kind of model you're going to look for, is it like polynomial models using trig functions or other user-defined functions? Mm-hmm. And then Piscini will use these past regression algorithms to try to find the smallest number of terms in this dictionary of functions, so that you get a model that you can interpret, and then you can use like real-time forecasting or feedback control, for instance.
Great, thank you. And as a follow-up question related somehow to machine learning, I've seen one of your recent publication, and I'm just going to ask you this very silly question: is why is the cylinder flow a terrible case for deep learning?
So that's actually the talk of my the title of my APS talk back in, I think it was Atlanta. So that was probably 2018.
Yes.
And that was very provocative. And
obviously,
I think I made a few enemies, or few people were not really happy with it. The reason why the cylinder flow is a terrible test case for deep learning is pretty simple. And I should say that when I say the cylinder flow, I really mean the low Reynolds number two-dimensional cylinder flow. The reason simply is because it's too simple. From a fluid dynamics point of view, it may be complicated, because there's if you compute the stationary solution, the fixed point of the equations, you get this very long reverse flow region, recirculation bubble behind the cylinder. You can do the stability analysis. You get the eigenmodes, which are somewhat shifted downstream of the cylinder. And as you use this as initial condition for a simulation for a DNS, the whole reverse flow region starts to shrink, and the structure, the eigenmodes start to deform into the POD modes, for instance. And this is I'll have to say, it's a fairly complex problem. But from a dynamical point of view, it's really simple. Because if you look at the eigenspectrum of the linearized Navier-Stokes operator at the fixed point, it has only a complex conjugate pair of eigenvalues, which is unstable. And so from a mathematical point of view, that's basically you have a two-dimensional linear subspace where the dynamics are unstable. And there's this theorem in dynamical system theory that states basically, I'm a bit oversimplifying, but that if the system has a two-dimensional, if the fixed point has a two-dimensional unstable subspace, then there's a two-dimensional nonlinear manifold which is tangent to it, and the dynamics are going to evolve on this two-dimensional manifold. So from a dynamical point of view, you really need only 2 degrees of freedom. That's the only thing you need to describe the whole cylinder flow. And that kind of makes sense, right? You would need one for the amplitude of the vortex shedding and one for the phase. And if you do things correctly, even with some kind of POD analysis, but kind of like a conditional POD analysis, where you condition on the amplitude of the drag, for instance, you'll be able to get the deformation of the coherent structures from the stability mode to the POD modes. And this embedding gives you precisely a 2-dimensional manifold. And on this manifold, if you use Cindy, for instance, to get the equations, you get a really, really simple system. It's called a Stewart-Landau oscillator. It's the simplest form of self-sustained oscillator. And so from a dynamical point of view, that's really the only thing there is, right? It's just a very simple Stewart-Landau oscillator. And so one thing that really bugged me was that not so much now. I think there's like fewer publications like that. There's still a few of them, but fewer. 5 years ago, there were a lot of publications using fairly complicated neural networks, like like up to a dozen different layers and stuff, using the cylinder flow as an example. And it worked on the cylinder flow, and then they were making, I'd say, some kind of unsubstantiated claims that, well, their whole architecture is going to work for high Reynolds number turbulent on a layer. And that's not really the case, because if you think about it, the only thing that these papers have shown is that these very complicated neural network could approximate a second-order differential equation. That's the only thing the evidence is supporting. It was not supporting any of the other claims they were making. So that's why it's a terrible case for deep learning. The 3-dimensional turbulent flow, cylinder flow at high Reynolds number is a different story. But low Reynolds number is just too simple of a problem for deep learning.
Great. Well, thank you. Very nice discussion. May I ask you about reduced order modeling? You've done a recent paper about the dynamic reduced order modeling framework, and I was wondering if you can tell us a little bit more about this, and eventually, how does it compare with more conventional model decomposition like DMD and POD?
So what we're doing with different colleagues, so Steve Branton is one of them, Bern Noack, who moved in China, is another one of them. We're basically trying to push all the standard linear decomposition techniques to their limit. So first things first, for instance, DMD until recently, I mean, just a few years ago, actually, up with the optimization problem that is actually DMD. And it turns out, for instance, that POD and DMD are very closely related because they're just special instance of the more general optimization problem. So what we're really doing is trying to push this to the limit of what we can do with linear algebra, basically. And we're also trying to take into account, so this decomposition, one of the major drawbacks, for instance, is that they're not very robust as you change the Reynolds number. Or if, for the case of the cylinder flow, you have data from the fixed point all the way to the limit cycle, the structure is going to change depending on the amplitude of the distortion. And this requires a lot to capture properly. I think for the cylinder flow, it's like something 2 modes if you want to capture really the whole thing. And so what we're trying to do is just extend all these techniques, but to basically parameterize them. So add the ability to get a POD decomposition that is parameterized on the Reynolds number so that we can get the deformation of the modes as a function of the Reynolds number in a sort of a continuous way, right? So we could interpolate between different Reynolds numbers. So that's one thing that is still work in progress, but we've had a few success with that. Once again on the cylinder flow, because that's the simplest case, right? If it doesn't work on the cylinder flow, it's very unlikely to work anywhere else. So at least it works on the cylinder flow. That's sort of our baseline test case. And then with burnt, we've also started to look at using other kind of observable to build our reducer models, because POD modes are nice, but they require full state information, right? You're able to observe the flow in the whole fluid field. And so in a simulation, that's fairly simple to do, but it's still costly in terms of memory or storage, because you need to store all these snapshots. And in an experiment in academia, it's kind of doable, because now with the whole improvement of PIV measurements and other fluid visualization techniques, you can actually do high quality POD analysis or BMD analysis from experimental data. But the problem is that these techniques cannot be deployed in industry, right? If you take a plane, you're not going to have a PIV, stereo PIV camera mounted on top of the plane. So we try to think about what are the physically accessible observable, like the lift and the drag, for instance, which are fairly simple to estimate even on a real wing. If you just have a bunch of pressure sensors, you can estimate these quantities and actually build the models from these measurements. So we're kind of bypassing the problem of trying to get the coherent structures, but really trying to build a research model from the signature of these coherent structures on whatever measurement we can actually have access to, even in a realistic setting. And so that's where it differs a bit from standard approaches based on POD Galerkin projections, for instance.
Great. Well, thank you very much. I have one last question, and possibly another one is, so my understanding is that, well, for your research, you are trying to use as less computational resources as possible, obviously. And some of us, like me, we are trying to use as much compute power as possible. I was just wondering if you have any comment on the race to running simulations on the next generation of supercomputer exascale computers. What's your view on this race to run very, very large simulation when you are doing research to try to use as less resources as possible?
I think it's needed, right? I still need data in the first place. I need it, whether it is from really high quality experiments or really high fidelity simulations. I do need data before I can do anything. If I don't have data, then I'm just doing nice math, but it's just math for the sake of math. So I think it is needed, and also for the whole stability, like my first area of research, this is something we're closely looking at, because as we have access to a larger number of CPUs or GPUs or even TPUs now with Google, well, we can do even more complex geometries, right? We can do stability in even more complex geometries, and we can start to basically do geometry which are of industrial interest, right? Rather than a fairly simplified model, we can actually start to do real industrial grade geometries. So I'm actively looking into it. The only thing I'm a bit scared, but that's maybe because I don't know much about really high performance computing, is that, like, generating data for the sake of generating data, if the only thing you get from these calculations in the end is just like mean profiles and error mass profile, that's kind of a loss, I believe. So I think the development of this code should also be done in mind with what are the data people who are not going to run these codes actually need, because I'm not going to run a calculation on 100 CPUs, but I may need the data for that in a fairly accessible way. So yeah, I think it's a good thing. And from what I've understood, there's kind of the community is kind of focusing on a few options in terms of different codes. There's not like 20 years ago where everyone had his or her own code. The whole open source paradigm forced people to work a bit more together on just like a few well-identified projects, which I think is a good thing.
Great. Well, thank you very much for your time and for your inputs. And we wish you all the best with all your future research and your future endeavors. It was very nice talking to you. We didn't talk much about exascale, but we talked a lot about stability and some software used to study stability of turbulent flow. That was, I think, very helpful for our community. So thank you very much.
My pleasure.
Thank you very much, everyone, for listening to this podcast. As usual, you can find us. Just Google UK Turbulence. You will find the website for the UK Turbulence Consortium website with all the link to the podcast, or you can find us on Twitter, UK Turbulence, the same name. So thank you, everyone, for listening, and hope to see you soon in a new episode.